Okay, so in this video then we are going to have a quick look at the halogens. So in terms of AS level, there isn't a great deal of questions they can ask on just purely halogen based chemistry. They can certainly link it into a range of different topic areas, but in reality there are very few pure halogen questions that we need to be worried about. However, I'm going to go through a couple of questions where these sort of things come up and run through the best practice in order of trying to answer them. So here's one of those questions. So this one is all about the reactivity of the halogen. So it tells you here that they're going to supply you with solutions of the halogens and the halides, sodium chloride, bromide, and iodide. And this is actually quite a generous question because it even tells you what the color of each one is in cyclohexane. So that takes a lot of the guesswork out for you. And all you got to do is plan an experiment on a test tube scale to show the trend in reactivity, include all observations and an equation for just one reaction, which actually makes things a lot easier. So essentially then, in order to do this, okay, hopefully, you've got to, you can use your own knowledge for this question. Okay, you should be aware, okay, based on what you may have learned at AS level, that the order of reactivity decreases down the group. So it's not a stretch to say, well, chlorine is more reactive than bromine, is more reactive than iodine. That much is obvious. You should know this. You can use your knowledge for that. So to simply, work out the reactivity, what I'm going to do is use displacement reactions. Okay, so displacement is what we've got. We can only use what we've been given. So we've only got solutions of each of the elements and the halides, so it must be displacement. So all we've got to do is add chlorine, add Cl to sodium bromide and sodium iodide separately. And the reaction will take place because, for example, I'll just do one of these to highlight to you what this is. So for sodium bromide, you're going to have Cl2 plus NaBr goes to essentially NaCl plus Br2. And then you're going to get two of those. Now, this isn't an ionic equation, so don't be tricked into thinking this is the equation you need. This is not ionic, okay? I'm just going to get to that in a minute. But this is telling you what's happening. So you start with chlorine and chlorine's color. Now, notice these are the colors of the individual elements, not the compounds. So in terms of observations, okay, chlorine will start off pale green, so your solution will be pale green, okay? Your salt solutions, your NaBr, NaCl, NaI, are all colorless. So they do not have a color to worry about. So the color change for this reaction is pale green to Br2 is produced, which is orange. So that's your observation. So you add chlorine to NaBr, you go from pale green to orange. And for iodine, for the NaI, it's the same thing, only this time the color change that you will see is pale green to violet. Nice and straightforward. And then the only other equation you will need to do, or the only other test you need to do, is adding Br, adding bromine to NaI. And the color change is going to be orange for bromine to violet for iodine, which is produced in the reaction. And that's it. That's all you need to say, because all the other reactions won't produce a result. So there'll be no other reaction. So you can, you can write no other reactions produce observations. And this essentially proves produce observations. And you can then link that to the idea that, well, chlorine can displace bromine and iodine, and bromine can displace iodine. So this is the correct order. Chlorine first, then bromine, then iodine. Only other thing you need to do is produce an ionic equation for any of the processes. So I'll take the equation I wrote at the top here, chlorine and bromine, in terms of making the ionic equation, you seem to have to get rid of the sodiums. So the ionic equation, okay, so sodiums will cancel effectively. So if you're unfamiliar how to write ionic equations, you take anything that's aqueous and split it into its ions. So NaBr would become Na plus and Br minus. and then the basic rules of mass apply. If anything appears on both sides of the equation, you may cancel it. So what that means is, I will go through the whole thing. Okay, Cl2 is not aqueous, it's just a liquid, doesn't split into ions, so it stays as it is. Okay, now when we balanced it, we had two of them, so I'll keep two there. So 2 sodium plus and 2 Br minus is what is produced there. And then if we do the other side, we have 2 Na plus again, and 2 Cl minus plus Br2, which cannot be split. Cross out the sodiums, they appear on both sides. The bromines do not cancel because these are not the same thing, which leaves you with your final equation. Cl2 plus 2 Br minus goes to 2 Cl minus plus Br2. Okay, any of the three equations will get you the mark of the ionic equation if you do it correctly. So yeah, 5-mark question this. Very, very straightforward. Okay, be careful with the observations. Remember that you are producing, okay, bromine in this equation, so the color must turn orange. Okay, chlorine is displacing, so it will lose its pale green color, and you're making bromine to make orange. It's a very common mistake for these colors to get swapped around by accident. So moving on then, another ionic equation. Okay, bromine is used to extract iodine from a solution. Write an ionic equation for the reaction. Again, a solution, doesn't matter what it is, it's the same as the one we've just done. Okay, so bromine is used, so Br2, and we are extracting iodide ions, so I minus, and we are making, okay, we're extracting iodine, so we must be producing I2 and Br minus. And again, quick bit of balancing, nice and straightforward. These ionic equations are always the same. They always look the same. They're very, very straightforward to write when you get used to them. So why is bromine less reactive? Sorry, why is iodine less reactive than bromine? Very, very similar to questions on periodicity and things like that. Only a few points you need to actually put down here. So iodine is bigger. Okay, so iodine, larger atomic radius, if you want to use the key words there. Okay, large atomic radius. You've also got more shielding. Iodine has more shielding. And therefore it's harder to attract an electron to fill the outer shell. Harder to attract E minus. That'll do for 3 marks. Okay, so larger atomic radius, more shielding, therefore it's harder to attract an electron despite the increase in nuclear charge. Okay, the shielding outweighs the nuclear charge. Okay, so I will just put outweighs nuclear charge just as an extra point, because there is an increase in nuclear charge. And the size also outweighs the nuclear charge. So the 2 factors there, bigger atomic radius and more shielding. This outweighs the nuclear charge argument, and therefore it's harder to attract an electron. So there you go. As I said, these questions on halogens are very, very straightforward. They don't ask a great deal of different things about them. If you're lucky, you'll just get something that's effectively a GCSE question pop up. But it's definitely worth knowing how to put down a good answer, okay, including all observations and equations, to make sure you get all the marks available.